Justin Miller, Oxford College Physics. We're going to continue onward now. We want to be looking at some spherical mirrors and image formation. So, here we go. There's a black pen. Let's go ahead and get started with this, shall we? Spherical mirrors. So, there's basically two types of spherical mirrors. Two types. Concave, which is something like this. This is the mirrored side, or the reflective side, if you will. And convex. Outer portion of the spherical surface that is mirrored, reflective, if you will. So here we have ourselves a concave mirror, and concave mirrors are pretty cool because they do some neat things. You may be able to see that certain things are inverted, upside down, if you will. I can put my face in here, and if I can get you in the picture there, my face is upright. But as we showed before, hey, it just kind of depends on some things. We'll be looking specifically at this. So concave, and then we've got ourselves convex. We've got this outer portion of the spherical surface is mirrored, and everything looks upright. There's this diminishment in size of things. Things seem a little bit smaller, but you got this wide spectrum of view here. As you can see these in like liquor stores and stuff, right? Hanging up so they can see everybody. But anyways, these are the two types of mirrors that we're going to be looking at. Convex, concave. And, well, we need to know some certain things about how they behave and certain consequences of things. So, what can we do? Well, we've already discussed that images are formed where light rays either physically intersect or trace back to a point of intersection after the reflection has occurred. So that's important. So, can we just apply the law of reflection to, say, concave and convex surfaces? The answer is, yeah, of course, it's the law of reflection. Things reflect off of surfaces at equal angles about the normal of the surface at the point of, well, contact, or consideration for that matter. So, well, let's just go ahead and look at some things, shall we? How about this? So there's a specific line or ray that's really important. We're going to look at that right now. There's a couple of them. This one happens to be pretty important. And we'll say, consider a ray that is passing through or is aligned with the center of the sphere that makes spherical surface of the mirror. So if we were to draw this nice circle here, it's harder than it seems sometimes, but I'll just approximate a circle. That's a pretty bad circle, but hopefully you can bear with me here a little bit and say, okay, well, that's a circle. Should we try one more? That's not much better. Those look like eggs. Well, it's pretty close to Easter. Anyways, let's use this one. This one's not as bad. Let's say that this is a circle that has some radius r, right? Well, let us consider some ray that is either aligned with or goes through this center here. Well, let's just make it go through, right? So consider some ray goes through the center. So what can we say about how that interacts with the surfaces? So take this. Take, for instance, this to be the mirrored side. This outer surface right here. what angle is this ray striking that surface at that location with respect to the normal of that surface? That's right, 0 degrees with respect to the normal. It's at normal incidence. It's completely radial. It's aligned with the radius itself. There is no angle, it's a 0 degree angle. So this one strikes at normal incidence. All right, so let's just go ahead and consider this ray that, or this isn't the surface of the mirror, that this is the mirror here. So this ray is like this. Well, what angle is it striking right there at? Well, again, if it's aligned with the center, then it has to be completely radial, which means that it's striking at normal incidence. So what can we say about a ray that is either aligned with or goes through the center of a spherical sector, if you will? It's going to strike at normal incidence. So, a ray that is aligned with or that goes through center of curvature will strike at normal incidence. So what does that mean? Well, it means that if it strikes at normal incidence, it's just going to reflect back upon its original path. If this is the mirror right here, this ray strikes and then it reflects back off along the same line. If this is the mirror right here, this ray strikes and just reflects off at the same path that it was originally taking. So that's important because we can utilize that. So let's just go ahead and see if we can make some sort of depiction here of what would happen for a specific case. And that specific case is going to be a concave mirror. So let's consider a concave mirror. Erase this up here real quick. All right. Consider an image being formed with a concave spherical mirror. What we know again that images are formed where light waves either physically intersect or trace back to a point of intersection. So let's just draw out a little depiction here. I'm going to freehand this. It gets a little bit messy looking, but we still get some sort of depiction here. So let me try. That looks like a much better circle than I did before, huh? So I just want the center here, center of the circular sector. So we're going to say that that is the center of this portion here. This was just for a guide for me. So here's our concave mirror here. Concave mirror. Center of curvature, C. And then we're going to draw in a nice principal axis. And the principal axis goes through the center of curvature and through the mirror at normal incidence. It's again for alignment purposes. So I'm just going to kind of draw this in. It's a nice straight line. Again, it's here to help us line stuff up. We're just going to go, this is principal axis used for probably an E that doesn't belong in there. There we go. Used for alignment. Goes through the center of curvature and goes through the mirror at normal incidence. So just to put things on. And then we're going to put an object on here, shall we? Well, again, with objects we usually use arrows because they have an orientation with them. And I'm just going to draw an object here. Object arrow. We'll use O's for objects. That's nice. And what we want to note is light is emanating from this object. And within these bounds here, down to here, light from the tip of this will interact with the mirror and reflect off in various different directions. But as long as we're along one of those reflected paths, we'll be able to see the image of the tip of this arrow. So that's what we want to look at. So we need to be able to have some way of gauging what some of the light rays do. Because if we can see where they either trace back to intersect or where they physically intersect, we can have a nice depiction of where the image is going to be located. And, well, there's one really nice one that we just discussed, the one that goes through the center of curvature. And then that just reflects back upon itself. So let us draw that in blue here. Say, we've got this light ray. It's going to go, again, let's consider the tip, because if we can do it for the tip, we can do it for everywhere. We can consider this ray right here. It goes like this. What does it do? Well, it's incoming. It comes and strikes the mirror. It's going to strike at normal incidence because it goes through the center of curvature, and then it's just going to reflect back upon itself. And there we go. There's one of the rays, very well founded by the fact that this is a spherical surface here. So we need one more ray. If we can find where two rays intersect, they all should be intersecting at that location. And there we go. We can figure out where the image is going to be located. So there's a ray. Let's get one more. What else could we do? How about we utilize this principal axis here? This principal axis cuts through the mirror at normal incidence. And we know that rays will reflect off at equal angles about the normal. Well, that's going to be an easy one then, because there's the normal to this location right here. What if we consider a ray that's going here, strikes at this location? What's it going to do? It's going to reflect off at the same angle. That's nice. So I'm going to draw this one in a green. Green's a little hard to see, but should still be able to see it here. So this ray, again, considering it going from the tip, and then into the intersection point of the principal axis and the mirror, and then it will reflect off at equal angles about that principal axis. And I'm going to just try to do the best that I can here with a little approximation without having to measure things out. And that looks semi-okay. Maybe not perfect, but hey. So there's the reflected ray, there's the incoming ray. That looks pretty decent for equal angles there. So we've got these two rays intersect right here. Well, that means that that is where the image of the tip of this object is located. Everything else will translate back to the principal axis this way, and there is our image, I. Intersection of the light rays. Now I could draw in a whole bunch more and say, well, if there's one that hits here, what's it going to do? It's going to reflect down here. There's one that hits here, what's it going to do? It's going to reflect up there. They're all going to reflect through this path. And then what do we have? Why is that the image? Because that's where it seems like light's coming from. Light actually is coming from that spot. This we have the physical intersection of light rays. From here, light diverges outward in all directions. No matter where you are, over on this side, as long as the light can enter your eyes, that's where you see the image to be. That's great. That's what we want to be able to do. So what we want now is to be able to name some things and start to figure out exactly how we can mathematically approach this. So let's just do that, shall we? let us name some distances here. Let us name the distance from the object to the intersection point of the mirror and the principal axis as the distance P. So this distance right here, I'm just going to translate this down. So everything is really measured along the principal axis. And this distance from the object to the principal axis, to the intersection point of the principal axis. Object distance, P. What else could we do? Well, we could have ourselves an image distance. Image distance from the image translated along the principal axis. And we're going to call that Q. What else could we have? How about from the center of curvature? The center of curvature along the principal axis. Let's call that R, the radius of curvature. Distance from the center of curvature to the mirror. Well, those are three pretty nice and easy things to be able to want to look at. That's great. There's a couple more things in here though. Let us say we've got some H. H is going to be the object height. And then we're going to take an H prime and say that that is the image height. This is going to get a little messier than I'd like right now, but I'm just going to draw an H prime there. H prime, image height. All right, so we've got a bunch of distances, basically, heights, distances, all kind of mapped out, named. What else can we do? Well, how about we name some angles here? Shall we? Sure. How about we name this angle here? Name that some angle, let's call it alpha. Well, if this is an angle alpha, this also has to be that same angle alpha. Because well, we just got one line going through a straight line. Alternate interior angles, if you will. And we've also got these two angles over here, this angle and this angle. Well, we know that those have to be equal angles by the law of reflection. Let's call them theta and theta. So we got some angles named in there and some distances. Let's see if we can make some mathematical connections between these quantities now. Excuse me. All right, so let's pull out some triangles. Up and down. Let's just pull out some triangles, shall we? All right, so what do you want to look at first? How about we look at this one? I'm going to take this triangle right here. Biggest triangle all the way. That triangle right there. And we're going to take this little triangle as well. Oops, no we're not. Not that one yet. Sorry, this one. Got this big triangle with the object and this little triangle with the image, and we got those two angles stated there. So I'm going to pull out this big triangle first, the top one, and we have this. We've got that this is theta, this is H, and that's P. All right, and then we got this little triangle as well, which we have, drawing it a little bit bigger, but we've got this angle, theta, this is H prime, and that's Q. So we've got those two triangles for us that we're pulling out of there, and what we want to do is make some sort of representation mathematically of correlation between some of these quantities here. So what can we say? How about the tangent of theta is equal to H over P? The tangent of theta is equal to opposite over adjacent, H over P. All right, that's good. What can we say about this one? How about the tangent of theta is equal to opposite over adjacent, H prime over Q? Well, we got two descriptions of what the tangent of theta is, because those thetas are the same. One thing I'm going to add in here, I'm going to add in a negative right there. You know why? Because this one's below the principal axis and this one's above the principal axis. And that allows me to gauge something about the orientation of things. So since that's below, I'm going to call it negative h prime. Great. Well, if we have the tangent of theta is this, and the tangent of theta is that, they have to be equal to each other. So from this, we've got that h over p is equal to h prime, negative h prime over q. What can we do with that? Well, we can write something else out. How about we solve this out for the quantity of h prime over h? This then says that h prime over h is equal to negative q over p. H prime over h, does that have any physical significance? This is the image height divided by the object height. Hey, this is something that has some significance. It's the ratio of the two heights. This is known as the lateral magnification. If the image height is exactly the same as the object height, hey, magnification is 1. There is no change in its the dimensions. But if h prime is greater than h or less than h, we have a diminishment in size, an enlargement in size or diminishment in size, respectively. So we define lateral magnification as m is defined by h prime over h. Image height to the object height, which happens to be equivalent to negative q over p. The negative sign there tells us something about the orientation, and well, the ratio of the image distance to the object distance is the same thing as h prime over h. Interesting. All right, so that's one thing that we've got. That's good. Let's see if we can do something else. We've got some other triangles in there. Right, yes we do, yes we do. Let us look at, I wish I had more colors. Yeah, I'll try this one. All right, got the brown here. Try it out. We've also got this triangle here. And with it, we have this triangle here. Both having these angles alpha. So let us write something out. We'll draw that first big one out. We've got ourselves this. We've got h, we've got alpha, and then we need this distance right here, right? This distance right here. How can we name that distance? Well, what happens if we take this distance p and we subtract off of it r? Oh, we're left with that. So that distance is going to be p minus r. P minus r. Fantastic. Let's look at this little guy right here. We've got this little triangle. We've got an h prime, we've got an alpha, then we've got this portion right here, which is this. What if we take this distance r and we subtract off q? That's what we're left with. So let us draw that one out. So we've got r minus q, we've got an h prime, and again, we've got an alpha. This h is above the principal axis, this h prime is below the principal axis, so we'll end up calling that a negative. But let's just go ahead and look at this. We can again look at the tangent of a theta, tangent of alpha in this case. The tangent of alpha is going to be opposite over adjacent, which is h over the quantity of p minus r. Great. We'll come over here, and then we've got ourselves the tangent of alpha is going to be negative h prime divided by r minus q. Again, negative because of the orientation. Well, again, we've got another tangent of the angle is this, and the tangent of the angle is that sort of scenario going on. So from this, these have to be equal. We've got ourselves h p minus r is equal to negative h prime divided by r minus q. What happens if we go ahead and solve this out for h prime over h? Shall we? So we can put this h over here, we'll throw in a negative sign on the other side, and we can write that h prime over h is going to be equal to, this comes up here with a negative sign in it, we've got a q minus r divided by p minus r. Here we go. There's another expression for h prime over h. Now, this one's not quite as useful by itself, because this is a lot more simple. Nonetheless, we've got h prime over h. All right, so let's take a look at this, shall we? A second. All right, so got some room now. Let us go ahead and look back at these. These two terms have to be equal to each other. They're both h prime over h. So what can we write? We can write, that negative q over p is equal to the quantity of q minus r divided by p minus r. And we can start playing around with this a little bit and seeing what we can do. How about we take this term, stick it up here, and take this term, stick it down there. So I can write this then as p minus r over p is equal to q minus r over negative q. Well, let's get rid of that negative q down there on the bottom. Kind of expand some things out. So we'll just flip the order of those. And we can write this then as p minus r over p equals r minus q over q. Good, good. What can we do with that now? We can start breaking things apart. We can write this as p over p minus r over p. Let's do that here. P over p minus r over p for this. And we'll break this one up. This has to be equal to r over q minus q over q. That's good. Well, what's p over p? 1. What's q over q? 1. So we've got ourselves 1 minus r over p is equal to r over q minus 1. Well, let's get the ones on one side and the other terms on another side. So we'll take this. I'm going to take this one. I'm going to take this one, this negative one, add 1 to both sides. That becomes 2. Then I'll add this term onto both sides. So we've got ourselves that 2 is going to be equal to r over q plus r over p. All right, we can factor out an r, right? This is going to be equal to 2 is equal to r times 1 over q plus 1 over p. And then we can divide both sides by r. And we're going to write this out now like this. 1 over p plus 1 over q is equal to 2 over r. That is a nice expression there. Nice and simple, nice and straightforward. This says 1 over the object distance plus 1 over the image distance is equal to 2 divided by the radius of curvature. So if we know, say, what the radius of curvature of our mirror is, and we know where we place our object, we know where the image is going to be. That's great. If we can figure out what the image of where that's going to be, then we can also figure out what the magnification is, negative q over p. That's exactly what we want to be able to do. So that's pretty much that for getting this expression. It just comes down to being a matter of using it at this point and looking at some other things that go along with it. So we will get one other thing before we start doing other stuff. And that is going to be looking at what is known as focal point. Focal point is defined as the location where parallel light rays either converge or trace back to a point of convergence. Let us define the focal point. is the location in which parallel incoming light rays will either converge to or trace back to a point of convergence after the reflection has taken place. So that's it. So what we want to do is look at this little scenario here. Keep that down a little bit. Erase this, bring out a little demo that shows that. Draw something else out. One sec. Just start grabbing a couple things really quick. Quick. There's that one, there's that one. All right, I got him. Don't break. Slow down. All right, I got a little light box here, a little laser light box. Hopefully you can see this decently. Got some laser light. Let me turn these big lights off and see if that helps. It's got these other ambient lights on. All right, so this laser light box produces some parallel light rays, and I've got these two pieces right here which are mirrored. One is concave, and one is convex. And what we want to do is look at those parallel incoming light rays do when they interact with this spherical surface. Well, look at that. Light rays bounce off, and they all come to this point of convergence. That is the focal point. Parallel incoming light rays reflect off and converge to that point. So that is going to be the case for concave mirrors here. They have a point where all of the reflected light rays physically intersect after they reflect. So that's pretty cool. What about a convex mirror? Let's take a convex one and kind of look at that. Stick a convex mirror there. Well, with a convex mirror, we've got the light rays are going to strike it and they're going to diverge outward because of the orientation of its surface with respect to the parallel incoming light rays. So no matter what, we get this divergence. But if we trace back all of these paths, there would be this one little point over here where they all intersect, but it's traced back. They don't physically intersect there. The reflected paths trace back. We still define that as the focal point of the mirror itself. So focal point's important because it does something in particular with parallel incoming light rays, or light rays that are parallel to the principal axis. Basically the same sort of thing going on. So what we have is something nice that we can utilize. Turn the lights back on here. A note, focal point, I'll drop a little scenario of what we just saw. Concave mirror. Concave mirror, got a principal axis there. We can take some parallel incoming light rays. What we do red. And point right there is F. Call F the focal point. Well, there's also a distance from F to the mirror along the principal axis. We call that lowercase f. That is the focal length. That's how we define the focal point for a concave case. We'll draw out a convex case too. Convex mirror. Got this. This one gets a little bit messier, but that's okay. Take this and say that this one goes off this. This. So this one goes off like this. This one goes off like this. Take one more. This one goes off like this. I'll trace back to this point. If I pass trace back to intersect at the focal point, it too has this focal length, which we define the same way, and that's pretty much that. So, we did look at this case, right? We looked at this case, we derived specifically the relationship between the radius of curvature, the object distance, and the image distance. We didn't use the focal point at all. We will. We didn't look at this case, though. Well, it turns out that we could do the same thing that we had done in getting those expressions for the object, image distance, radius of curvature relationship, and gotten the same results. 1 over p plus 1 over q is equal to 2 over r for the convex case. But in order for that to be true, we need a specific sign convention. So this is another important aspect of things, sign conventions. Conventions, different class. Sign conventions for mirrors. So we're only going to be looking at single interactions for now. So with single interactions, we'll always have that the object distance is considered positive, but ultimately, object is on the front side of the mirror. P is equal to a positive quantity. The object on the back side, it's negative, but for a single interaction that doesn't make any sense. The front side is the mirrored side. So then we got the image. Image is on the front side of the mirror. Q is a positive value. Image is on the back side of the mirror. Q is a negative. Image on the back side. All right. Then we've also got the radius of curvature. So center of curvature on the front side. R is considered then to be a positive quantity, and this would be concave mirror. And then we have center of curvature on the back side. Where the radius of curvature will be considered to be a negative value. And that would be, since we've got convex mirror. And excuse me, also got H prime is positive, image is upright, H prime is negative, image is inverted, and that pretty well sums up those for the most part. So we've got that. And then we've got another relationship between focal length and the radius of curvature for spherical mirror. For spherical mirrors, focal length is equal to 1/2 the radius of curvature. F is equal then to a positive value for a concave mirror, because R is positive, and F is equal to a negative for a convex mirror. And furthermore, we can write out that 1/P plus 1/Q, it is equal to 2/R, but that's going to be the same thing as 1/F, which is a little bit even simpler than we had before. So we've got this, and then we've got the lateral magnification. Magnification is equal to H prime over H, which is negative Q/P. And again, because H prime can really be negative or positive depending on whether the image is upright or inverted, that really comes down to the side of the magnification. If M is equal to positive, image is upright. If M is equal to a negative, the image is inverted. Absolute value of M is greater than 1. The image is enlarged, bigger than the object. And if the absolute value of M is less than 1, image is diminished. In size. Ooh, that pretty much sums up all those sign conventions and the correlations between certain signs and certain quantities. All right, so that'll be it for now.